Yes, hi everyone, thanks for the introduction. As already said, my name is Michael Strunk. I'm a PhD student at the University of Salzburg under supervision of Verena Bögelein and also Nayan Liao. First of all, please let me thank the organizers for arranging this workshop in this nice environment that is the ESI here in Vienna. Okay, so today I'm going to talk about gradient regularity results for so-called widely degenerate parabolic equations, and a lot of what I'm going to talk about is very similar to what Mr. Tsubuchi just talked about. Okay, so let's start with the setting. We consider degenerate parabolic equations of this type, so in divergence form with a right-hand side f, and as usual we consider this equation in a space-time cylinder omega t, taking over some spatial bounded domain in Rn for some finite time capital T greater than 0. Also note that we include a right-hand side f. This right-hand side f is only assumed to be assumed to belong to this good enough Lebesgue space. So Ln plus 2 would be critical. We need a bit better. So we assume Ln plus 2 plus sigma for some arbitrarily positive sigma greater than 0. Okay, note that the vector field in the diffusion term of the equation is provided as the gradient of some function f. And this function f, non-negative function, is of course assumed to satisfy certain structure conditions. So first of all, we assume that f is constantly equal to 0. So f vanishes entirely for any gradient variable in some ball. Let's say ball with radius 1, unit ball. Moreover, we require that f is convex with respect to the gradient variable. Also with respect to the gradient variable, we need C1 regularity everywhere, in particular at the unit sphere. And we need C2 regularity, at least if we stay away from the unit sphere. Within the unit sphere, I mean, f is 0 there, it's obvious. And we need it outside, but the C2 regularity may break down at the unit sphere. And also note that we allow an x dependence, so there we also need some regularity where we assume that the vector field, the gradient of f, is Lipschitz with respect to x, and that does satisfy this Lipschitz bound with a constant that is not quantitative. It's only a constant that is finite as long as this psi is somehow controlled for some finite L. Okay, and these conditions already basically justify the denotation as widely degenerate, but we need more. We need some ellipticity or coercivity, and this is the second condition we need, which is quite general. So let's consider some small positive delta, usually 0, 1. And what we assume is that we can control the smallest eigenvalue of the Hessian of f from below by some constant that is going to depend on this delta, and also we can control the largest eigenvalue from above for some constant C2 depending on delta. At least we can do so for any gradient variable that lies within this annulus. So first of all, the upper bound is only local, it's not a global bound for the Hessian in general, so as long as this psi is somehow controlled. And also we can only do so if we stay a little away from the unit sphere. So this is the problem set, So as long as we have this lower bound for the modulus of psi, 1 plus something, 1 plus this arbitrarily delta, In particular, C1 and C2 are going to depend on this delta. And in general, we may lose ellipticity when we pass to the limit, delta to 0, whereas what I said, the Hessian is not assumed to be bounded globally, it's only a local bound, So this may blow up when delta approaches 0. So either we have a problem basically at the unit sphere or for large gradient values, Okay, note that we could allow any radius for the ball. For simplicity, let's consider unit ball, And this large set of degeneracy will, as we will see in a second, have an impact on the regularity of solutions, Okay, so we need an example now. Let's consider the so-called model equation, where once again the vector field in the diffusion term is provided as the gradient of some positive function f, here denoted as f of p, for the usual growth parameter p greater than 1. And this simply arises from this specific choice f of p. And we easily see that this equation and this choice of f looks very similar to the well-known P Laplacian, but there is this cutoff denoted by this positive part. So we discard small gradient values. Any gradient value in the unit ball does not count. We don't see it. And as I said, in particular for this sort of widely degenerate version of the parabolic P Laplace equation, we will not get the C1 alpha regularity in general. Okay, moreover, let's check our conditions. So the regularity assumptions are satisfied, and then for simplicity, let's consider the case p greater than 2, but holds for any p. And then for any xi in this modulus, annulus that I introduced, for any delta positive, we can control the smallest eigenvalue of the Hessian of f of p from below by a constant depending on delta, and now also on this parameter p. And from above, yeah, again, a constant depending on delta and p. And here we can nicely see what I told you before, that we lose ellipticity when delta approaches 0. Since now this is the superquadratic case, this happens at the unit sphere, whereas the Hessian blows up for large gradient values. If p would be equal to 2, then we have a sort of degenerate version of, widely degenerate version of the Laplace equation. Then if we are in this annulus, okay, then the constants are simply 1. They do not depend on delta. If p is smaller than 2, then we have similar estimates, but then the Hessian blows up when we approach the unit sphere from outside, right? Whereas we lose ellipticity for large gradient values, yeah. Okay, next, let's talk about our employed notion of solution. So it's nice that we can consider such a general setting, but this comes at the cost. Namely, in general, we do not have any quantitative growth estimates, right? So we have a lack of structure, and therefore we have to start a priori with weak solutions that are locally Lipschitz. There is no way around this. We cannot prove the gradient boundedness without any quantitative growth information. Okay, then we call U a weak solution if the usual integral identity is satisfied for any smooth and compactly supported test function zeta. Okay. However, if we have growth, for example, for the model equation, this is the case. Here we have p growth for large gradient values. Yeah, here we could start with the usual LPW1P notion of solution. This is no problem, yeah. But in general, without any growth, yeah, we can't start with a weaker notion of solution. Okay, next, let's talk about the interesting thing, the regularity of weak solutions. So we can quickly check that if we consider the homogeneous version of the model equation, that is, if we put f to 0, then we see any Lipschitz function with a Lipschitz constant bounded by 1, that is time independent, solves the equation weakly. But this is a problem, because therefore we simply cannot expect better than Lipschitz in general, right? In particular, we cannot expect C1 alpha, in general at least. This leads to a lack of regularity arising from this large set of degeneracy. And okay, so now we cannot get Lipschitz better than Lipschitz in general, but I told you we consider locally Lipschitz functions, so this looks strange, right? However, we can still get better than Lipschitz. We can still get some C1 regularity result, but this cannot, at least in general, concern the solution U itself, right? Because small gradient values, they do not count. The equation doesn't see them, doesn't give any information. So this large set of degeneracy allows the solutions to behave a bit naughty for small gradient values. However, what we can basically show is we can show the C1 regularity outside of the unit ball. That is in the set of points where the gradient lies outside. Or more generally, what we can investigate and also prove, we can prove that the composition K of du, rather than du itself, that this is continuous for any continuous function K that discards small gradient values, such that K is equal to 0, let's say. Because that's exactly what we want, right? Small gradient values, they do not count. And yeah, this is basically the natural function that we investigate, yeah. And indeed, I'm not the first one to do so, but there are some regularity results that dealt exactly in this setting. So the composition K of du has been shown to be continuous by a number of authors. In the elliptic case, this was started by Sant'Ambrogio and Vespri, as the former speaker already explained, and this was done for the planar case, n equal to 2, and by Colombo and Figali generalized for arbitrary space dimension. They considered a similar general setting, but the function f only was allowed to depend on the gradient, not on x. But okay, still nice result, of course. For the model equation, we can do so even for systems. So in the vectorial case, this has been shown by Bögelein, Duzza, Chova, Passarelli, Di Napoli. And for some model type equation, this was done by Leon Mons, who considered a bit more general setting than the model equation, again for systems. Okay. In the parabolic case, to my knowledge, the only C1 regularity results, so there are some other results, the Lipschitz continuity for the model equation has been shown, and I think also some Sobolev regularity, but in terms of C1 regularity, the only result, to my knowledge, is again due to this aforementioned authors, once again for the model equation and for systems. So for the model equation, I introduced you a few slides before. Okay, since this holds true for the model equation, yeah, it's natural to inquire whether we can get the same regularity in the more general setting. And basically, this was my aim of investigation. And yeah, the question can be answered positively, and this is the main result of the talk. So recall, we consider right-hand side f at least in ln plus 2 plus sigma, and u locally Lipschitz solution to our structure conditions, so the regularity assumptions and this widely ellipticity condition. Now also in the case where we can allow an x and t dependence. Yeah, and then we get the same regularity result. Not the gradient itself is continuous in general, but this composition k of du is continuous for any continuous function vanishing in the unit ball. Okay, great, we get the same result. And for example, as an easy corollary, I mean, one of the continuous functions that vanish in the unit ball, we already have, right? For example, this vector field. If we impose a little, let's say, continuity everywhere, I mean, we could also just consider the continuity with respect to the gradient, then we would not need this assumption. But let's say this is nice. Okay, then we can plug in the gradient. And then this vector field, of course, now as a mapping to Rn, this is continuous. Yeah, so this is nice. At the very end of my talk, I'd like to provide a remark on the optimality of this result, but basically the former speaker already did so, but I will still do so. Before that, I will talk about the idea of the proof. How do we get this? And this is again similar to the ideas from the former speaker. So first of all, it's clear that we have to overcome this general lack of ellipticity, right? Because without this, we cannot do anything. So for this matter, let's introduce the first scaling parameter, epsilon, let's say small, 0, 1, and we do local estimates. Consider some parabolic subcylinder, QR. And what we do is, the usual comparison argument. We consider the unique weak solution u epsilon to this Cauchy-Dirichlet problem, where u epsilon takes the original solution u on the parabolic boundary of the subcylinder, and u epsilon does not solve the original equation, but rather this enhanced version of the equation, where now note there is this additional Laplacian scaled with this small scaling parameter epsilon. Okay, why do we do this? Because this equation is nicely uniformly elliptic. Of course, in general, with an ellipticity constant that is going to depend on this epsilon. But still uniform elliptic, okay, then we can employ the standard method of finite difference quotients to obtain the existence of second-order weak spatial derivatives that are square integrable locally. Okay, and this is of course important if we want to do any C1 regularity. Next, we need a second scaling parameter, this delta. And what this delta basically does is, it allows us, or this we need in order to somehow make use of our ellipticity condition. And what this G delta function does is, Mr. Tsubuchi already introduced it, but this is a little bit different because now we do not have a problem at the origin only, but in the full unit ball. So somehow this measures not the distance, not to the unit ball, but to a little larger ball with radius 1 plus delta. Okay, and then what we show is that the composition G delta of du epsilon for any delta and epsilon, this is locally Hölder continuous with Hölder exponent and Hölder constant that depend on the data in particular, as this denotation suggests they are going to depend on delta, this we cannot avoid. but fortunately they remain independent of epsilon. This is important. Why? Because of course somehow at some point we wish to pass to the limit. If we can do everything independently of epsilon, then we can first pass to the limit epsilon to 0 to obtain that this limit function without giving the details. This is for any delta still Hölder continuous, such that we can also pass to the second limit delta to 0, to obtain that this limit function, which now looks good, because this measures the distance to the unit ball, not to a larger ball anymore, that this is locally uniformly continuous. And basically, once you have done this, you get the main regularity result, so the continuity of the composition for any continuous function vanishing in the unit ball, relatively quickly. And Mr. Tsupuchi already explained that exactly at this point you lose information. It's not really clear what the best modulus of continuity of this limit function is. But I will provide a remark on this at the very end of my talk. Of course, now it's difficult, or the main difficulty is how to get the local Hölder continuity of this G delta of du epsilon function. Okay, for this matter, we again do local estimates. So let's consider another subcylinder with radius 2 rho, vertex Z0, compactly contained. What we show is that this Lebesgue representative, this gamma Z0, limit of the mean value, that this exists, and that we have this quantitative L2 excess decay estimate for G delta minus this Lebesgue representative. So we can control this L2 mean value from above by up to a constant by the quotient of the radii with power 2 alpha. And this is essentially the Hölder continuity once you have done this. Of course, it's not clear how do you get this gamma Z0 and this excess decay estimate. Okay, as I said, we wish to do everything independently of epsilon, so it's clear that somehow, basically before we start, we need a uniform L infinity gradient bound for u epsilon with respect to epsilon. So I do not go into detail here. Basically, this you can do, and this uses a nice trick of Colombo and Figalli, and this heavily relies on the fact that you consider a priori Lipschitz solutions. Okay, but I won't go further into detail. Once you have done this, okay, then we do the same trick as before. We choose some mu greater than 0, such that we can control du epsilon from above by 1 plus delta plus this mu. This we can do. Okay. Somehow we want to get this Lebesgue representative at Z0. So what we do, we consider a sequence of nested cylinders around this point, where the radius is divided by 2 in each step. And then what we do is, in each step of the iteration, so in each cylinder, we distinguish, or we decide rather, whether a certain measure theoretic information applies, or whether the reverse information applies, because one of the two has to apply. And basically this is in the spirit of Di Benedetto and Friedman's pioneering results for parabolic P-Laplacian systems, where I also mentioned Di Giorgi and Uhlenbeck. Okay, what are these two regimes? The first is the so-called non-degenerate regime. Second is the degenerate regime. Non-degenerate regime, this is basically the nice case. And as the name suggests, it's the case where du epsilon is non-degenerate. So basically this holds if the subset of points where du epsilon is relatively near on a set of large measure. Somehow we are near the supremum, basically we are away from 0. So this holds if we can find some small parameter nu. This nu is usually very small, such that if du minus 1 plus delta, this we shift to the left-hand side, the bound is mu. If we are a little away from this upper bound, this can only happen if this holds or appears on a set of small measure. So somehow we are already almost everywhere near the sup. So the equation then is non-degenerate basically. Okay, in the degenerate regime, the reverse holds true, such that whenever we are a little away, this indeed holds true on a set of, this has, this subset has a certain amount of measure, Basically, the idea is now how do you combine both regimes, And basically, this is the last part of the proof. And the results stated on this slide, the majority of the article basically deals with these results. So this is the main, the hard part. Okay, what we can do in the non-degenerate regime? Basically, as I said, somehow it seems we are non-degenerate, so we should have a lower bound, and we do have. So we can prove that this du epsilon is controlled from below by 1 plus 3/2 delta, almost everywhere, at least on the next step of the iteration. So on the cylinder with radius half the radius before. But what this tells us is the equation is uniformly elliptic with respect to delta only. So we can nicely discard the epsilon contribution of the Laplacian. Okay, and recall we have second order weak spatial derivatives. So if we differentiate the equation, we can show that this partial derivatives du of u epsilon for any I from 1 to n, this is a weak solution to a linear parabolic equation, where the coefficients are elliptic, uniformly elliptic, and bounded, where the ellipticity only depends on delta now due to this lower bound. So we can throw away the epsilon contribution. And this looks good. Linear equation, uniformly bounded coefficients. Yeah, then we can use known results and infer relatively quickly that this back representative, this gamma set not exists, and that we get this claimed L2 excess decay estimate for G delta du epsilon. So basically, once the non-degenerate regime applies, we're finished. This is the nice case. However, it may of course happen that in each step of the iteration, the degenerate regime applies, right? Because nobody tells you otherwise. Okay, in this case, we cannot get a priori the same nice result as in the non-degenerate regime, but we still luckily can get the right estimate in the end. So what we can prove is that this function denoted by v, which again somehow measures the distance to the ball with radius 1 plus delta, now with the scaling of the equation inherent, that this is a weak, not solution, subsolution to a linear equation with, again, uniformly elliptic and bounded coefficients. And then due to the fact that we have a subsolution, we cannot proceed as before. What we can do is basically up to a translation, we can show that this function v belongs to a parabolic de Giorgi class, and then overall we derive a so-called expansion of positivity. What's this? This is a tool that somehow converts measure theoretic information, which I recall this is the thing we have, and translates it into pointwise estimates. And basically this in the end allows us to obtain a reduction of supremum for G delta of du epsilon, once again on the next step of the iteration. So this G delta of du epsilon, this decays with a certain rate. We could state the rate, but I did not here, because it's not so important. Only what this says is, if the degenerate regime applies in each step, we have this decay. But then this gamma set not still exists, right? Because it's 0 due to this reduction of supremum on each step. So this decays. Okay, and once you know that this gamma set not is 0 and exists, you again infer relatively quickly that this excess decay estimate holds true. And then, as I explained, this is essentially the Hölder continuity. And then by passing to the limit epsilon first and then to delta second, we get the continuity. And as my very last 2 points of the talk, this is what I already hinted. By passing to the second limit delta to 0, we lose information. And this limit function, it's not clear what the best or the optimal modulus of continuity is, right? Maybe it is Hölder continuous, maybe not. But this is not even known for the model equation. So somehow it's not clear. Maybe it is Hölder continuous or not. It's just not known what the best modulus of continuity is. Okay, and as my very last remark, natural question, what happens if our function k is nicer? Let's say k is Hölder continuous or Lipschitz continuous, rather than only continuous. Do we maybe then get the Hölder or Lipschitz continuity of this composition? But unfortunately, this fails in general. So there is a counterexample due to Colombo and Figalli, which prove there exists Lipschitz function k, essentially this one, such that this composition is continuous, but it's not Hölder continuous for any Hölder exponent. And therefore this result is optimal in this sense, and unfortunately you cannot get better in general. Maybe for the model equation you can, but in general you can't. Basically it doesn't matter how nice your K is, you can always destroy this with a quite rough degeneracy near the unit ball. But okay, still we can get this regularity result, which is still nice. And yeah, this is the end of my talk. Thanks.
Thanks for your very nice talk. Are there comments or questions or remarks? Yes.
Thank you. I have a question. So when you think about avalanche dynamics, then what would happen is that you have no movement until a critical slope is reached, and then suddenly it switches on. So there would be discontinuity in this function f that you have, while you're assuming C1 continuity, I think.
Yeah, okay.
So in this case where you have discontinuity, could you still say something, since, I mean, it's sort of believable, since in the way you capture regularity, you're ignoring the set you don't like, so you could sort of make a smart choice of your function k and still get away with something, or is this completely out of reach?
Yeah, you mean you basically can overcome this by staying always a little away from the problem set. This you mean probably, yeah. Maybe, I'm not sure. It could be possible, but I'm not sure if there is some problem at some point. I'm not sure. Maybe yes, but I need the C1 regularity in the way I do it, but maybe you do not actually. But I'm not sure if there is some problem somewhere.
Other questions? Oh, yeah.
You can go some two slides before. I mean, yeah, this one.
Mm-hmm.
I think that, okay, I remember that in a paper with Tomokus, we have something very similar, right? That we have, we do this measure theoretic stuff. We do, I mean, just when, without the absolute value, but that's the same because we do sub and sub solutions, right? That we say if you have something in measure, then it's uniformly elliptic at the next stage. I think this is similar to what you're doing, right? I mean, there's
yeah, maybe I should have mentioned this, but exactly this idea builds upon your paper.
Yeah, exactly. And do you think you can have also potential estimates? Because we did also, I think so, right? I mean,
I'm not sure, unfortunately.
I think so, because you should have, let's say, some intrinsic potential estimates for the quantity that you are considering under the sign of divergence. I think that this is locally bounded by the risk potential of the right-hand side, the caloric risk potential.
Thanks. Yeah, unfortunately, I do not really know a lot of potential theory in general.
I think so, that it should work, because also we have this, I think if this scheme is working, because at this stage, this is the same scheme that we had in this, and then you could, maybe this you could look at in a future work, yeah, right.
Yes, okay, thanks, yeah.
Other questions? Okay, then if not, we thank the speaker again.